as well. So now separation techniques had to do a lot about the solubility of substances. Which substances are soluble, which ones are insoluble, and everything pretty much depended on that. That was one of the major factors in separating substances. So an example, an important aspect of chemistry is purity and methods of purification. Give an example of substances used in everyday life which must be pure. So one obvious example is
Medicine.
medicine.
Yes, if it's impure, it might harm the user.
Nee, but the problem with medicine is, I mean, I know why you're saying medicine, but uh, a lot of medicines are actually a mixture of different things. Uh, they're not usually not a very pure substance. I mean, it's a mixture of different things. I mean, there are two or three different things added in medicine. Most of the medicines. Uh, so I, I mean, one very obvious example should have been water. I mean, you want water to be as pure as possible. You can't really guarantee 100% purity of anything in the real world. Uh, but for water, it should be pure. And I think when we're doing desalination, I told you that large particles. You're going to study air and water in a later chapter again. You filter it to remove sand and dust particles. Desalination or reverse osmosis or simple distillation is done to get rid of the salts. And what's left is you also add charcoal and chlorine. I mean, charcoal is added to get rid of smells, odors, bacteria. It's if there are any smells or taste, it improves taste. And then chlorine is added, like in swimming pools, it's added to kill bacteria. So you treat water with a lot of things. So water is one thing that has to be pure. As anyways, moving to the next one, and let me also open the board very quickly. Just a second, just for reference. As I'm coming back to this from the list, so water from seawater, that should simple distillation should work for this. You evaporate the water and then you condense it at the other end. Uh, So simple distillation would work. Reverse osmosis would work for that, but that's not given as an option. Helium from a mixture of helium and methane. Now, for this, I'm going to tell you. I mean, if you don't know right now what helium and methane are, they're both gases. Methane is the gas that. I mean, you're going to learn about methane in later chapters, much later on. Right now, if you see any compound, just Google something about it so that you're able to answer this. Methane is the gas, is the cooking gas that it's for domestic heating. Your heaters, etc. They run on methane, and helium is the gas that you fill balloons with. So both of them are gases, and their formulas are helium is has a mass of 4 in the periodic table, and methane is CH4. So if you add up the atomic masses, carbon is 12, hydrogen is 1. So that would give you 16. So that gives you 16. So diffusion, you're going to use diffusion for this. Why? Because if you and this is what we did when we were doing separation techniques. So this board pretty much has everything. So this was the last thing that we did. I told you that heavy gases, they travel slowly. So if you have a very long cylindrical pipe or any container and you pass those gases through it, the lighter ones would travel much faster and you'll be able to collect them earlier, and the heavy ones would come a lot later because they're slow. So diffusion. Then ethanol from a mixture of ethanol and propanol. They're both alcohols. And they're both alcohols and they're both soluble in each other. So for that, you're going to use fractional distillation, specifically fractional distillation, because uh, just like ethanol and water, ethanol and propanol, they have different boiling points. One would boil first, the other one would come later on. So this one would be where's fractional distillation? This one would be fractional distillation. Uh, then iron filings from a mixture of iron filings and water. Now, iron filings is small bits and pieces of iron, like iron nails. Now, that they're not soluble. I mean, from general knowledge, you must know that iron is not soluble in water. So, you can simply do filtration. So, for that, you're gonna do filtration. And then I told you about amino acids. I told you that uh, for amino acids, you use chromatography. Chromatography is specifically used to separate dyes and also other biological substances like sugars and amino acids. And for amino acids, the thing is that they're not visible, they are invisible. So, which is why you need to spray the chromatogram with locating agents, because otherwise, you won't be able to see the spots that are forming. And I said, then you have, so that was the last one, that was chromatography. And I told you about crystallization. I told you about this last thing. He's saying, how would you obtain a pure sample of copper 2 sulfate, 5 water crystals from a mixture of copper 2 sulfate, 5 water with copper? Now, this one, you don't know both of these substances. So I'm going to tell you first. Uh, and don't worry if you don't know this, because we haven't learned this at the moment. Uh, Now, copper 2 oxide is a solid. ठीक है? Much later on, you're going to learn about solubility of substance. So it's insoluble. And copper sulfate dot 5 water, that is, I'm just going to write, not solid, I'm going to write this one as insoluble. Okay? So it's like marble. That's Marble is insoluble. You mix or chalk, you mix chalk in water, it doesn't dissolve. Copper sulfate is like NaCl. You mix it in water and it dissolves. So one of them is soluble, and the other one is not soluble. Now, copper compounds are going to come a lot in chemistry. So, just to have some familiarity, because later on you're going to learn about the colors of these compounds as well. So, copper 2 oxide is this black chalk like substance, just like chalk, it's not soluble. So, this is copper 2 oxide, and copper sulfate, they are blue colored crystals that are very soluble. So somewhere they would. So this is how. This is what happens. You have this crystal just like a salt crystal. A salt crystal is NaCl is white. Copper sulfate, on the other hand, is blue, and you dissolve it in water, and it turns into a blue solution. It's completely transparent. It completely mixes. So, so just to give you an idea, because copper compounds are going to come up a lot in a lot of these questions, especially the past paper questions. And now again, I'm just repeating, don't worry if you don't know them right now. TK, we're going to learn about them much later as well. So one of them is insoluble and one of them is soluble. So I'm just going to, just for your convenience, I'm going to change these. Let's think of NaCl, that's the normal table salt, that's soluble. And think of chalk, which is calcium carbonate, and that is insoluble. So how do you think you'd be able to separate them? Like one of them is insoluble, the other one is soluble.
Maybe first by filtration.
To give so I mean that's how you're going to do that, because the insoluble particles would be filtered out. uh, so the first thing that you're going to do is, now you have to write the whole thing. I mean, you've been given these two samples. Okay, let's just keep it that way. Let me get rid of this. So you're given these two substances, you're going to mix copper 2 sulfate, uh, and you're going to mix and stir in water. So what would happen when you mix and stir in water? The copper sulfate, which you saw, would quickly form a blue solution. That would be your copper sulfate aqueous. And the copper 2 oxide that you just saw, the black substance would all be settled at the bottom, because that's not soluble. Make it black. I mean, there is black. So the black copper 2 oxide would still be So that's the first thing. You're gonna mix and stir in water and then filter. And then filter. So what's going to happen? You're going to filter it. So you're going to take a a funnel, and at the bottom of this funnel, the blue copper sulfate would pass straight through because that's soluble and it has completely dissolved. And in the separating funnel at the top, you'll have a residue of copper oxide. So the black copper oxide would be stuck over here. Uh, so you filter. So that's the second point. Now he's specifically asking, how do you obtain a pure sample of copper 2 sulfate crystals? You don't want copper sulfate, you want crystals of copper sulfate. Now we've gotten a solution of copper sulfate. So what's the next part? Now you have to answer questions systematically and carefully. You have to answer exactly what they're asking for. Uh, don't write stories about it. You just mix it in water. You use a separating funnel, and copper 2 oxide will not dissolve because it's insoluble. So it's going to be stuck over here as a residue, and the copper sulfate would pass straight through. But right now, you haven't gotten crystals. So the last part is, how do you make crystals? And this is something we had discussed earlier, crystallization. And I specifically asked you to remember this is apparatus. Just a second. Where's crystallization? So this part over here. I specifically told you that there are two ways of forming crystals. One is evaporation to dryness, where large crystals are not formed. But crystallization is you evaporate some of the water solution, not all of it, and you let the particles join up, and you cool them gradually to and allow crystals to form. And then you filter out those pure crystals, and you dry them between filter papers. So this is exactly the last part that you're going to write. That and this is called the filtrate. So you're going to write that evaporate the filtrate to saturation point. Okay, and you're going to use the exact, remember, don't use, this is the filtrate. Use the word filtrate. It's a 4-mark question. You have to be careful. You have to sound scientific. That's the first thing. So evaporate the filtrate to saturation point and cool gradually. And once crystals are formed, and filter out crystals formed. And since in the question he was very specific that he wanted uh, crystals, so you dry them between filter papers. So that's it. That's the whole thing. Mix and stir in water, and then filter, and then evaporate the filtrate that you get, and to saturation point, and cool gradually, and filter out the crystals, which are formed. Now, this crystallization process would come a lot. It comes a lot in chemistry. The end part is always filtration, crystallization. So it comes very often. So is this clear? The previous question.
Yes, sir.
Okay. Next one is a similar question. The first one is butane from a mixture of propane and butane. Now, both of them uh, are gases. Uh, Propane and butane, but this time there is diffusion actually. So butane from mixture of propane and butane. So that in that one, diffusion would work because both gases would have. You have propane. You must have heard about propane gas and butane gas. So these are also used for heating, and for a lot of times they also use for domestic heating as well. So oxygen from liquid air. That is going to be now. Remember, it's liquid air they're talking about. Now, air I told you is what? It's nitrogen and it's oxygen. So you have a container, and there's liquid air in it. Both of the gases are. I mean, if it's liquid, that means it's the container is at a very low temperature. So they're going to have different boiling points. I mean, both substances, nitrogen and oxygen, they're going to have different boiling points. So for that, you're going to use fractional distillation. And this is something also part of air and water, but I'm going to add this. I'm going to add this point in fractional distillation because with fractional distillation. So I'm just going to add this. There's a chapter at the end, but it's related to this, so I'm going to add one point over here. Uh, like you have oxygen tanks in hospitals. So liquid air is separated into its components by fractional distillation. There's because once air is liquid at a very low temperature, and you can liquefy air if you get the temperature really low. So there's going to be liquid air, and you can simply heat it up, and first one of the gas it evaporates and boils, and then another gas boils, and you can collect those gases separately. There's another thing about fractional distillation, which is there's another thing that uses fractional distillation for separation, and that's crude oil. Again, crude oil, it's part of organic chemistry. We're going to learn that much later on. Uh, but I'll just give you a very brief overview of this particular example and fractional distillation. Just a second. So, crude oil is the oil that you obtain from the Earth's crust, and it's a mixture of many different things. So, what happens is, uh, let me just open this image. So what happens is that it's a mixture of many different gases, and they all have different many different liquids as well. You've got lubricating oils, you've got diesel, you've got kerosene, you've got naphtha, you've got petrol. So it has different components. So that is exactly how they do I mean, they do something similar to fractional distillation, which is that they heat it up and they condense it at different temperatures. There's at the bottom there's residue which is used for roads. You've got fuel oil for ships. So many different things, waxes, uh, petrol for cars. All of these things are obtained from the black colored crude oil that's obtained from the Earth's crust. So that's another application which we're going to study much later on in organic chemistry when we study organic chemistry. So remember, fractional distillation, there are two major applications. One is liquid air, that you can separate the air into its components, oxygen and nitrogen, and the other one is oil can be separated as well. So we're going to add that. So crude is also separated, sorry, into components using the same technique. Okay, not going into a lot of detail yet. Uh, as a next one, you've got water from aqueous magnesium sulfate. Now, magnesium sulfate is a salt, just like NaCl. Uh, and aqueous means that it's soluble. Aqueous means that it has dissolved. So how do you obtain water from a solution that has salt in it? That is going to be simple distillation. Okay, when you use simple distillation, and where is simple distillation? Simple distillation is when you have a soluble substance in a solvent, and you want the water or the solvent. The water evaporates and you collect it at the other end, and the solid salt particles, they would remain behind. So simple distillation is used in this specific case. ठीक है, ये सारों को समझ आ रहा है? Do you get it? Any questions? Turan, is this clear? Asita?
Yes.
Okay. So then you have potassium chloride from aqueous potassium chloride. Okay. This is again like table salt, but again it's soluble. But now he's asking for the salt. So if I just revise this part, if you have a soluble solute plus solvent, like we did it with NaCl and water, if you want the salt, you can either evaporate to dryness or you can do crystallization. And on the other hand, if you want the solvent, you can do distillation. There were three methods, and one was reverse osmosis or desalination. So now he's asking for the crystals. He's asking for the salt. So either evaporate the water or you do crystallization. So let's see what two options do we have over here. I think there's crystallization written over there. So to get the salt crystals, you're going to do crystallization. So then you have silver chloride from mixture of silver chloride and water. Now, silver chloride, I'm going to tell you that's a substance that's not really soluble. It doesn't dissolve, just like marble doesn't dissolve or chalk doesn't dissolve. So it's not soluble. So if it's not soluble, you can simply, just like sand and water, you can simply do filtration. That's it. And then glucose from a mixture of glucose and maltose, that one is chromatography. Remember, biological substances use chromatography to separate them. Just like amino acids, just like sugars, just like any other biological substance, chromatography is often used to separate them. So next is exactly the same type of question. Again, you've got a salt. Aqueous means that it's already soluble, so it's soluble, and he's asking for water. You want water to be removed from the solution. So that would be simple distillation again. So the salt remains behind, and the water evaporates, and it reaches the other end. So that would be simple distillation. So just remember when to use simple distillation. Next one. Again, helium from a mixture of two gases, helium and argon, that would be diffusion. I mean, the two gases would travel at different speeds, so diffusion should be sufficient. And this time again, there's a soluble salt. Aqueous means it's dissolved, uh, and you want the crystals, copper 2 sulfate. So again, you're going to do crystallization now. You're going to get rid of the water and allow the crystals to form. And this is ethanol from aqueous ethanol. Aqueous means dissolved in water. So there's ethanol plus water. This is when you have two solvents and two solvents which are miscible in each other, like water and ethanol. So that would be fractional distillation. So then you have barium sulfate from mixture of water and barium sulfate. This Google barium sulfate. Barium sulfate is again something that's insoluble. So if that is insoluble, that would be filtration. You can filter it out. Okay, so is this clear as well? Turan, is this clear? Adil? Can you hear me? Saneem, can you hear me?
Yes, yes, sir. It's clear.
Acha. Acha, this next one, it's about changes of. I don't think it's a separation technique question specifically. He's asking which three substances. As he's asking which three substances are solids at room temperatures. Now, room temperature is 25. Now, I previously told you that if there's any temperature between the melting and boiling point, then the substance would be a liquid in the middle. If it's higher than its boiling point, then it's going to be a gas, and if it's lower than the boiling point, then it's going to be a solid. So first one, room temperature is 25 degrees centigrade. So where would you see 25? Like, is it Where is it? Is it between them, higher than this, or lower than this? 25 would come out to be, it's going to be the first one is going to be a solid. So can anyone tell me what would the second substance be at 25?
Solid.
It's going to be a solid again, because 25 is again below the melting point, so that's going to be a solid. So he's asking which these substances. So what about the third one? What state would the third one be at 25?
Liquid.
ठीक है, that's going to be liquid. 25 is coming in the middle. And this one at 25, what would it be? Okay, 25 is,
A solid.
okay, that's a solid. So ABN. So the answer to this is ABN D. The fifth one would also be a liquid. And what would this be at 25?
A liquid.
No, it's not going to be a liquid. Where does 25 is not?
Oh, wait, sorry. Would it be like a gas?
It's going to be a gas. 25 is much higher than the boiling point, so it's not in the middle. It's not lower than this. It's going to be a gas. So which one is an ionic compound? Forget that. Which one is a gas at room temperature? So it's this one, F. We just did that. There was only one gas at room temperature. Which two substances are liquids at room temperature? We've done that. Forget. Which one is out of all these five, which one is an impure substance? How do you know that a substance is impure?
If like the melting point is decreased and the boiling point is increased.
No, but more importantly, that was for water basically. Okay. The point was that pure substances, they have a very fixed melting and boiling point. Impure substances, their melting and boiling point they melt at a range of temperatures. Not just it's not fixed any longer. So this indicates that it's kind of impure because the melting point and boiling point are not fixed, and that's going to, so it's going to be E. The substance that's impure, why? Because uh, doesn't have a fixed melting or boiling point, although they didn't ask for the explanation. So it doesn't have a fixed melting point or boiling point. So anyways, moving on. As I explained why the chromatogram must be sprayed with a locating agent. Why? Because you can't see the amino acid. So to make the amino acids visible, and explain how it is possible to identify the amino acid from the chromatogram. So what do you calculate in a chromatography for identification purposes? क्या होता था? ठीक है, so you basically calculate RF value. And because I told you every substance has a unique RF value, so you calculate the RF value, and then and if you want to identify and match those RF values with known samples. Okay, so for identification purposes, you must have some known samples, and you can calculate their RF values, and then you can match. If two substances have the same RF value, that means they are exactly the same substance. So what's happening here? He's saying the equilibrium mixture leaving the reaction chamber contains 15%. Suggests how the ammonia could be separated from the mixture. That would be fractional distillation. You can, because they have different boiling points. Fractional distillation works. So suggest how the ammonia could be separated. So use the term, one mark would be for just using the term fractional distillation. So what you're going to do is, You heat the liquid, and different gases can be collected at different temperatures. I mean, which one would be the first one to evaporate?
Ammonia.
No, it's not going to be ammonia. Actually, it's. I mean, ammonia would.
Hydrogen.
It's going to be hydrogen, TK, because hydrogen would very quickly turn into a gas. Well, hydrogen would be a gas at pretty much all the temperatures above. Like it would be a gas at -50. It would be a gas. Any temperature that's above the boiling point of hydrogen, it's a gas. So almost every temperature is above the boiling point of hydrogen. So different gases are collected at different temperatures.
Also, sir, could we say that if we lower the temperature,
You
then
can,
ammonia will be the first one to turn to liquid?
take that's also a possibility. I mean, you can say that as well. So and and both are true. I mean, the both fractional distillation. You can either condense it or you can heat them up, and they would turn into gas. So both of them are exactly the same. Like in crude oil, you do the opposite actually. What you do is you're trying to lower the temperature actually. So different things condense at different temperatures. As anyways, this one is most helium obtained from natural gas found. Natural gas contains methane and helium. One possible way to obtain helium would be to burn methane. Now 93% would be methane, CH4, and he's saying that there is 7% helium in it. Okay, that's natural gas that you obtain from the Earth's crust, and he's saying that one method of doing that would be to burn the methane. Now, I told you just that methane is used as a cooking gas. It's the gas that comes in your heaters, in your cooking stoves, etc. So, why would it not be suitable? Just general knowledge. Why would it not be a suitable method to obtain helium? Like, does anyone know? And again, it's a completely general knowledge question. Like, what happens if there's too much combustion, like cars burning petrol, and does anyone know what happens? Like,
So, like the carbon dioxide, which is formed, would still be with the helium, so you wouldn't have separated the helium.
so Tika, that's a good point. But they're saying that. I mean, they've already said that there's. I mean, they're saying that's a method that works. So we're assuming that we're not finding faults with the method. Okay, what we are saying, why it's not a suitable method. The reason, so I'll just tell you, the reason it's not a suitable method is uh, that burning methane or burning gas. I mean, firstly, you're wasting 93% of it, right? I mean, that's a lot of. I mean, you can give it to homes. You can. Uh, it's your cooking gas. It's the gas for domestic heating. So you're wasting. It's very wasteful. Yeah, that's one thing because it was mostly methane, right? And he's just burning off all the methane. So that's like wasting a lot of stuff. The other thing is that that's why it's not suitable. Plus, burning or combustion causes global warming, like burning petrol, burning. So a lot of combustion, it it causes it causes global warming. So it has environmental effects. So he's saying suggests so diffusion would work. We know diffusion would work because and they're saying other than diffusion. Diffusion would work because helium travels faster, so you can collect helium earlier, and methane would be slower, and it would take a longer time to reach the other end. But what could be another method other than diffusion by which helium could be separated from the mixture of gases in natural gas? Does anyone know any other method?
So, could we use fractional distillation if turning the air to like liquid?
Okay, because most likely they're two different substances, so they have different boiling points. So you can definitely use fractional distillation. So one would boil or condense at a different temperature. The other one would boil and condense at another temperature. So fractional distillation could be used in that case. So you've got a chart paper now. It's a chromatograph. Why? So he's saying that there's an ester. Forget what ester is. But I'll just give you an idea what ester is. Ester uh, it's perfumes are made out of esters. Food flavorings, most of the things that you eat, they're basically esters. Especially the things that you eat. Uh, like if you're eating ice cream and you're eating strawberry ice cream, then that ice cream pretty much has nothing to do with a strawberry because uh, it's a molecule of an ester that's created in the lab that tastes like strawberry. So it's used in food flavorings. Like all the juices that you drink, they have nothing to do with. Most of the time, they don't have anything to do with the thing that's on it. Like apple juice, it's probably has nothing to do with apple. It's a molecule of an ester that's created in the lab that's added as a food flavoring. So so esters are these biological substances that are naturally present as well, but they use as food flavorings and perfumes. So anyways, just a brief introduction of what esters were. Uh, so he's saying he's using chromatography, and this it was sprayed with uh, bromothymol blue. So it's like a locating agent. Why do you? So it's a different locating agent. So why do you need to spray it with a locating agent? Because you want to make them. You want them to make the uh, esters visible. That's why you did it. And explain what is meant by the term RF value. So that is distance traveled by the dye divided by the distance that is traveled by the solvent. Or you can simply, because remember, no one is looking for stories in chemistry. It's you can simply write the formula. It's distance of the dye divided by the distance of the solvent, and you can add that from the starting line. Or you can just write all distances should be from starting line, which is the line that you made over here. Over here, they're calling it the baseline. So you're given these RF values and you're being asked to identify sample 1 and sample 2. So you're going to calculate the RF values for this. So what's the RF value for this one? So how many distance traveled by the spot, sample 1, divided by the distance that the whole solvent is traveling. So it's how many boxes? 1, 2, 3, 4, 5 boxes. So the solvent is traveling 5 boxes. I mean, assuming that's 5 centimeters, I think. And what is this? Probably how many boxes are there? That's 1, 2, 3. That's probably 10 boxes over here. So it's probably 1.1. So the RF value would be, what would you get if you do this for sample 1? It's going to be 0.22. Can somebody do this on the calculator quickly? It's probably 0.22.
Yes, sir, it's 0.22.
So that means that's tartaric acid. That's a I mean, they gave you a table, so you're able to identify that that one is tartaric acid. And similarly, you can calculate the RF value for the second one, which is 2.3, I think. So the distance. So that's 2.3 distance traveled by the dye divided by the total distance, which is 5. So that would be 0.46, I think. So sample number 2 has an RF value of 0.46, which is malic acid. So you're able to identify both of your samples. So is this clear?
Yes, sir.
Okay. So let's continue. We'll do some more questions. This worksheet was slightly difficult. Would be slightly difficult because it contains all these substances that you don't know anything about. Okay. So I'm just giving you a brief background of what those substances are. So we'll continue tomorrow with the same worksheet. Okay, then take care. Allah
Love you,
Hafiz.
sir.
Allah Hafiz.